Okay, we're going to talk about, we're starting chapter 1. We're going to talk about physics today, some units, basically the scientific process, and significant digits. So our learning goal today is that students will learn about SI units of measure, the scientific method, and significant digits. Okay, first of all, what is physics? All right, physics is the branch of science that involves the study of the physical world. Okay, namely energy and matter and how they're related. And we're going to spend the whole class, the whole course, just talking about the interactions of energy and matter, that they're essentially two sides of the same coin. And this is an undergoing study. I mean, there's so much we don't know. There's new energy and new matter that's discovered. You know, it's been discovered recently. You know, recently I'm talking about the last couple decades. We don't know really much about it, so we call it dark energy and dark matter. But there's so much to learn, and hopefully you guys are going to solve these problems and answer these questions. All right, so what career can you choose as a physics major? Well, you could be a scientist at a university and college, obviously. Industries hire physicists. Research institutes, they recruit physicists from you know, more prominent universities. I got my physics minor from Calvin. I was not recruited by a research institute. But nonetheless, I learned a lot of physics. You can go into other related fields such as astronomy, engineering, computer science, business, finance, and even medicine requires some physics. Okay, let's talk about SI base units. So we're going to use, for length in this class, we're going to use meters. We are going to use SI units. Mass, we're going to use kilograms. Time, we'll use seconds. Temperature, we have one unit in thermal energy. We'll use kelvins for that. The amount of substance, we won't use this often, if at all. You'll use this in chemistry. The unit would be mole. Electric current, we will use amps for that. Luminous intensity, we'll use candela. Okay, so the Bureau and the National Institute of Science keep standards of length, time, and mass, against which our meter sticks, clocks, and balances are calibrated. So here's a picture of a kilogram, the unit, the standard for a kilogram, and the standard for a meter, well, the old standard for a meter, which are made out of platinum iridium. Platinum's very chemically stable, and iridium is super strong. However, the meter now is defined differently. This meter, I'm sure it's aging, and I don't even know if they keep it up. I know the meter now is defined as 1,299,792,458th of a second. It's the speed that light travels in a vacuum, or the time it takes. I'm sorry, the distance that light travels in a vacuum in this time. Okay, we are also going to use these prefixes. Okay, femto, we won't use this very often, 10 to the negative 15th. Pico, we will use some. Picometer, for example, 10 to the negative 12th. We'll use nano quite a bit because all of our electromagnetic radiation will be in nanometers, the wavelength. Micro, like microgram, for example, we'll use micro a decent amount, 10 to the negative 6th. Milli we'll use, like for current, electric current. Milliamps is very common for proper unit. Centa, for centimeter, we'll use some. Deci, example would be deciliter. Kilo, 10 to the third. Kilometer we'll use for distances quite often. And then mega, giga, tetra. We won't use all that often. So next is dimensional analysis. Dimensional analysis is something we're gonna have an ongoing discussion about this. But basically, the units to a problem are extremely important. And we're going to use those units to work backwards to solve for missing quantities, to help us understand mathematical relationships better. So you might not use an exact version of a formula. You might use a couple different formulas to work your way through a problem. And the process will be called dimensional analysis. Okay. Next, let's talk a little bit about significant digits. The valid digits in a measurement are called significant, and they depend on what we use to measure. So all non-zero digits in a measurement are significant, but not all zeros are necessarily significant. Depends on where they are. We'll try some examples of that in a little bit. When you perform an arithmetic operation, it's important to remember that the result can never be more precise than the least precise measurement. Okay, that's why where standard significant digits come from in the first place. So if we add or subtract measurements or multiply and divide, we're going to have to round. We're going to have to round the same number of sig digits as our least precise measurement, or our least precise value involved. Okay? All right. Next is the scientific method. Here's the scientific method. Okay, we're going to make observations and do experiments and create models and theories to try to explain the results. So we're going to start with a guess, a hunch about the way something works, and we're going to then design experiments to come up with models, laws, and theories. We'll try to reproduce this in the labs that we do as much as possible, where I won't tell you guys exactly what to do. I won't tell you exactly what the theories and laws are that we're discovering, even though some of them are pretty common that you already know. But rather, we're going to just set up experiments. You're going to have to make a hypothesis in the lab. You're going to set up some experiments and test that hypothesis. And this is the beauty about science. This is why science is so awesome, in my opinion, is just the process, right? I mean, if we make a hypothesis of something we think is true, and the experiments don't line up with that, then we have to throw away our hypothesis. It doesn't become a law, a model, or a theory. Something only becomes a law, a theory, or a model if it passes experiments, and then someone else can set up that experiment, so that experiment will be reproducible and give the same results. And then therefore we can make predictions too with this science, which is so powerful. Another thing I want to point out is that models, laws, and theories are on the same level here, right? So the word theory many times is looked at as, well, in the English form, a theory is just like a hunch, right? I have a theory that something works a certain way. That's not how the word theory is used in science. In science, a theory is a well-established framework of ideas supported by a large amount of evidence. Okay? So let's look at some examples. The universal law of gravity, or the universal theory of universal gravity, right? So Newton described a theory in which all matter is attracted to itself. That's the universal law or universal theory of gravity. All right, it's true. We know that this is true because we've never observed anything to float, right? Things fall, things are attracted to one another, and if things do float, if things do start rising, where if we jump out a window and we rise, there's always an explanation for why that happened, right? So there's been no counterexample to the law of gravity or theory of gravity. Similarly with the theory of evolution, right? There's significant evidence to show that life evolves, all life. And over large periods of time, it evolves and even developed in a different species. This is a theory supported by incredible amounts of evidence, and there's no counterexamples to show that it's not true. So this is more than a theory. This is more like factual. Same thing with the germ theory of disease, right? It's called the germ theory of disease, but it's more than a theory, right? We know that disease is caused by microorganisms. It's not really a theory in the sense of the way we use the word. And I want to make sure that that's very clear so that we understand what a theory in science means. It's very different than how the word is used in the common sense. Okay, let's just try a couple example problems with sig digits in SI units. So let's say the potential energy of a body of mass is raised to a height h, and it's expressed mathematically as potential energy equals mass times gravity times height, where g is the gravitational constant, m is measured in kilograms for mass, and g is measured in meters per second squared, which is the acceleration due to gravity. All right, so height is in meters, potential energy is in joules. Then what is the joule described in base units? So basically, what is a joule? This is part of our dimensional analysis. We know that potential energy is measured in joules, and we know that mass is in kilograms. We know that gravity is in meters per second squared, and we know that height is in meters. So let's do that multiplication, and what do we get? All right, the answer should be C, right? Because if we write down the formula, potential energy is equal to mgh. We know that potential energy is measured in joules. We know that mass is measured in kilograms. We know that gravity is meters per second squared. We know that height is in meters. So we multiply this out, we get kilogram meters squared per second squared. That's what a joule is. This is our dimensional analysis. This helps us understand, okay, a joule is really this. It's really a kilogram meters squared per second squared. And this is a little more complicated, so we're going to call this a standard unit of 1 joule. You can see how this physics and this math works together and how this language is written. Okay, let's talk about accuracy and precision real quick. Let's say 3 people perform an experiment to determine the value of acceleration due to gravity on Earth, which most scientists agree is 9.8 meters per second squared or 980 centimeters per second squared. The following results were obtained. Ron got 961 plus or minus 12 centimeters per second squared. Kevin, 953 plus or minus 8 centimeters per second squared. And Paul got 942 plus or minus 4 centimeters per second squared. Who was the most precise and who was the most accurate? Okay, Ronald is the closest with to 980, so his is the most accurate. All right, and Paul only has a plus or minus 4 as far as his tolerance or his error in his experiment, so his is going to be the most precise. Okay, so there's a difference between accuracy and precision. That's important. Okay? All right, so we're going to start some homework. I hope this helps for now.